The absorbed dose is defined as where dE is the mean energy deposited by radiation per unit of mass, dm, of any material. The SI unit is the Gray, equal to 1 joule per kilogram. The absorbed dose from X and gamma radiation can be calculated as where the last variable is the mass energy absorption coefficient, defined in units of square centimeter per kilogram. This coefficient depends on energy and the medium, and represents the fraction of incident photon energy, E in joules, that is deposited in the matter. The first variable is the photon fluence or photon flux density, defined in units of per square centimeter, where dN is the number of photons incident on a cross-sectional area dA. Since biological risk depends on the quality of radiation, a quality factor is applied to modify the absorbed dose. Where the quality factor is a function of linear energy transfer, being equal to 1 for photons across the entire energy spectrum. This quantity is referred to as dose equivalent. The SI unit is the sievert, also equal to 1 joule per kilogram. The mass energy absorption coefficients can be obtained from the NIST database. Liquid water can be chosen as a good approximation to soft human tissue. However, we will select soft human tissue as the biological material of interest. This plot shows how the mass attenuation coefficient and the mass energy absorption coefficient vary in soft tissue. Both coefficients decrease with increasing photon energy. Low-energy photons experience greater attenuation due to a higher mass attenuation coefficient. In this energy region, the photoelectric effect dominates, leading to greater absorption. Consequently, incident photons transfer almost all their energy to the soft tissue. Thus, the mass energy absorption coefficient is approximately equal to the mass attenuation coefficient. In this energy region, the Compton effect dominates, leading to greater scattering. Consequently, incident photons transfer less energy to the soft tissue. Thus, the mass energy absorption coefficient is smaller than the mass attenuation coefficient. We will select this data to copy and paste it into an Excel spreadsheet. Selecting the values of interest for the determination of the absorbed dose and dose equivalent, which are the photon energies and the respective mass energy absorption coefficients. Where some values were interpolated for the gamma radiation energy of Cesium-137 and for the gamma radiation energies of cobalt-60. Only photons with energies above 15 keV, which are considered highly penetrating and thus relevant for ambient dose equivalent, will be considered. Next, we will also convert these photon energies to joules. We will also convert the tabulated mass energy absorption coefficients to units of square centimeters per kilogram. Multiplying each energy value by the respective mass energy absorption coefficient in soft human tissue. The plot of the product of energy and the mass energy absorption coefficient shows an increase with increasing energy above approximately 60 kV. Expressing the product of energy and the mass energy absorption coefficient in units of Gray, since 1 Gray is defined as 1 joule per kilogram in this context. Again, the plot of the product of energy and the mass energy absorption coefficient shows an increase with increasing energy above approximately 60 kV. We will now consider only the energy range from 15 to 3000 kV, which is most commonly used by radiation monitors. A relationship increasing with photon energy, starting from approximately 60 kV, continues to be observed. Now we will proceed with the calculation of the deep tissue dose equivalent for the specific case of a point source with an activity of 1 megabecquerel at a distance of 30 centimeters. Because the distance of 30 centimeters is large enough, the photon fluence rate at a distance of 30 centimeters can be reasonably approximated by the source activity divided by the surface area of a sphere, neglecting attenuation. Calculating the photon fluence rate, as previously mentioned. Note, the fluence rate calculation is arbitrary, since the shape of the previously established curve remains unchanged when multiplied by a constant fluence rate. While the numerical values at each point change, their relationships remain constant. That is, the value of the chosen fluence rate of 88.4 photons per second and per square centimeter for each energy value is arbitrary, as it does not affect the shape of the dose rate curve as an energy function. We will use the previously calculated values for the product of energy and the mass energy absorption coefficient, as they are specific to the photon energies and interaction material. Converting the absorbed dose rate from Gray per second to microgray per hour. The absorbed dose rate is calculated here in units of microgray per hour, and it was calculated as the product of the fluence rate, assumed constant across all energies, energy, and the mass energy absorption coefficient for each energy in soft tissue. The dose equivalent rate, as calculated here in microsieverts per hour, is determined from the product of the quality factor and the absorbed dose, where the quality factor equals 1 for photons of all energies. The dose equivalent rate decreases in the photon energy range from 15 to 60 kV, reaching its minimum value at 60 kV. And it increases with increasing photon energy from 60 kV onwards. Following this calculation, the dose equivalent rate due to a cesium-137 point source with 1 megabecquerel of activity at 30 centimeters distance was found to be 1.09 microsievert per hour. And the dose equivalent rate due to a cobalt-60 point source with 1 megabecquerel of activity at 30 centimeters distance was found to be 3.75 microsievert per hour. Because each cobalt-60 decay results in 2 photons being emitted with 100% probability. Let's check the dose rate values in the Radionuclide and Radiation Protection Data Handbook, 2002. Under the same conditions. This publication presents a deep tissue dose equivalent rate of 1.07 microsievert per hour, notwithstanding the small differences between bibliographic references. While the calculated dose rate is similar, it is not directly comparable to the specified value because the calculation did not incorporate the photon emission probability, which is not 100% in case of cesium-137. Again, under the same conditions. This publication presents a deep tissue dose equivalent rate of 3.86 microsievert per hour, notwithstanding the small differences between bibliographic references. That is, a value similar to the calculated one. Dose rates were normalized relative to the cesium-137 gamma radiation dose rate, at the same fluence rate, a common calibration reference. Inverting the normalized energy response curve, which is the ratio of the dose equivalent at the reference energy, cesium-137, 662 kiloelectronvolts, to the dose equivalent, for each energy value. The second graph presents the same data as the first, but with the energy axis displayed on a logarithmic scale. The calculated curve, normalized to 662 kiloelectronvolts gamma radiation from cesium-137 as a reference, is the theoretical dose rate curve in the absence of energy compensation. Therefore, it reflects the typical relative response curve of uncompensated energy detectors. Calibration of an uncompensated GM counter using cesium-137 gamma radiation, 662 kiloelectronvolts, establishes a known point of accurate measurements. The accuracy of measurements at other energies is not directly determined by this calibration alone. Uncompensated GM counters can theoretically provide reasonably accurate dose rate measurements for X or gamma radiation at or near 15 kiloelectronvolts, as the dose rate at this energy, assuming identical fluences, is similar to that for 662 kiloelectronvolts gamma radiation from cesium-137. Uncompensated GM counters are also capable of measuring higher energy radiation dose rates that satisfy the acceptance criteria. The acceptability of these measurements is determined by their energy response curves, which serve as guidance. Yet, uncompensated GM tubes calibrated for Cesium-137, 662 kV, overrespond significantly at lower energies, particularly around 60 kV, which tend to result in substantial errors in dose rate measurements. As shown in manufacturers' energy response curves, uncompensated GM tubes calibrated for Cesium-137, 662 kV, are subject to substantial dose rate errors for X and gamma radiation around 60 kV due to their energy dependence. However, it should be noted that the theoretical energy response curve doesn't perfectly match a device's actual energy response curve. Among other factors, the device casing and detector enclosure, like the walls of the Geiger-Müller tube, always cause some degree of attenuation or filtration. So when an uncompensated GM counter, calibrated to Cesium-137, is exposed to 60 kV gamma rays, for example, from a filtered Americium-241 source, it overestimates the dose rate. This is because it assumes the counts of these photons are from 662 kV Cesium-137 gamma rays, which would result in a higher dose rate, as has been shown. The result is an overestimation of the dose rate. An uncompensated detector, calibrated at 662 kV, will overestimate the dose rate below 662 kV and underestimate it above 662 kV, crossing over at this calibration energy. In a 2021 study, investigation into the performance of dose rate measurement instruments used in non-governmental networks, National Metrology Institutes found that all tested uncompensated Geiger-Müller detectors significantly failed to meet the requirements of IEC 60846, Part 1. All the tested MINs failed the requirement set by IEC 60846, Part 1, by a high margin. The behavior of the MIN types is expected as they utilize energy-uncompensated GM sensors. Energy-compensated versus uncompensated Geiger-Müller counters. Energy-compensated Geiger-Müller counters incorporate a filtration around the chamber, for example, 200 mg per square centimeter, that preferentially absorbs low-energy X-rays and gamma rays, resulting in a more flattened dose response. Although the energy response curve cannot be perfectly flattened, the filtration significantly improves response uniformity over the designated energy detection spectrum. Scintillation detectors. The key advantage of scintillation detectors is their ability to perform spectrometry. Because they can measure the energy of incoming photons, they are able to accurately determine energy-compensated dose rates. Atomtex brand, model AT1121. Scintillation plastic. Tissue equivalent detector. The detector's reference point is specified. Radiacode brand, model 103. Thallium-doped cesium iodide scintillator. The detector's reference point is specified. Atomtex brand, model AT6131B. Energy-compensated Geiger detector. The detector's reference point is specified. Gamma Scout brand, W Alert model, energy uncompensated Geiger detector. The detector's reference point is not specified. A dose rate between 1.48 and 1.49 microsievert per hour was measured at a distance of 5 centimeters from the surface of the Cesium-137 source. This dose rate is taken as the reference value. A dose rate between 1.45 and 1.52 microsievert per hour was measured at the same distance. A dose rate between 1.48 and 1.53 microsievert per hour was measured at the same distance. A dose rate of 1.49 microsievert per hour was established by adjusting the source distance to match the other readings. A dose rate between 0.23 and 0.24 microsievert per hour was measured at the same distance. A dose rate between 0.22 and 0.25 microsievert per hour was measured at the same distance. A dose rate of 0.17 microsievert per hour was measured at the same distance. We can assume a maximum error of -29%, which is within the device's specification limit of plus or minus 30%. Even when energy compensated, a Geiger detector is not as accurate as a scintillation detector across the entire energy spectrum. However, its readings are still generally acceptable. A dose rate between 0.42 and 0.54 microsievert per hour was measured at the distance previously determined using the Cesium-137 source. We can assume a maximum error of plus 125%, which is not compliant with the normative requirements. The dose rate overestimation was expected, as the Geiger tube is uncompensated for energy. When switching the filtration to measure other radiation types, such as alpha or beta particles, some devices do not automatically change the reading unit, as the filter switch is not electronically coupled to the unit display. Users must manually select the appropriate unit of measurement when measuring weakly penetrating radiation. Otherwise, readings will be in dose rate. Dose rate measurements are relevant for strongly penetrating radiation, such as X-rays, gamma rays, and even neutrons. In this device, when changing the filtration from X-rays and gamma rays to beta particles, the unit of measurement changes from dose rate to flux density. And when changing the filtration from beta particles to alpha particles, the unit of measurement changes from flux density to counts per second. Therefore, the user will not measure the ambient dose equivalent rate for alpha particles, as they do not contribute to this quantity. Alpha particles are unable to penetrate the skin's outer layer of dead cells. Measuring an ambient dose equivalent rate for alpha particles emitted from an Americium-241 source is pointless, as alpha particles are stopped by the skin. Moreover, the alpha particle count rate from Americium-241 is being used to calculate the dose rate as if it were from Cesium-137 gamma rays, leading to an incorrect value. For this type of radiation, measurements should be made in counts per second or per minute. In contrast to a dose rate at a specified distance, count rates, expressed in seconds or minutes, are not traceable quantities, meaning they cannot be calibrated against a reference. For a given radiation source, count rates depend on several factors. These include the types of radiation the detectors can measure, for example, photons only or multiple radiation types, the detector's intrinsic efficiency for each radiation type and energy, which depends on factors such as the physical form of the detector, solid or gaseous, the detector's size and sensitive area, smaller or larger. Thus, the count rate is a detector-dependent quantity that cannot be compared between different devices, except for devices of the same brand and model. The gamma-ray count rate measurement at contact with the Americium 241 source with the GammaScout device was approximately 1 count per second. This low count rate is due to the detector's physical form, gaseous, and the small size and area of the end window GM tube. The same measurement of gamma-ray count rate at contact with the Americium 241 source with the Radiacode device was more than 1,500 counts per second. This higher count rate is due to the detector's physical form, solid, despite the small size and area of the crystal. Even with the inclusion of alpha particle counts, the GammaScout is far less sensitive than the Radiacode device, which is much more sensitive for gamma radiation alone. A count rate measurement by itself doesn't tell us how hot a given radiation source could be, nor how dangerous it could be. Count rate measurements are useful for detecting radioactive contamination, even at low levels, including sources and contaminated items, by observing increases in background radiation. Furthermore, they can be useful for determining the activity if the detector's efficiency for the emitted radiation and the geometric measurement efficiency are known.